Welcome back. Now we're going to look at some examples, many of which follow from the things that we looked at in the first part of this lecture, a few of which don't, and along the way we will look at some other aspects of Java that turn out to be relevant. Okay, so number of cases here where I really want you to pause the video and make sure you know the answer to the question before you go on and let me tell you what the answer is. So what's this going to print? We've got two variables which are ints, and we are asking whether they are double equals. Do you know? It prints true, because values of primitive types, like int for example, are compared using double equals in Java. That's the only way to do it, and it does what you expect. Now what about this one? This time we're comparing strings. We're comparing one string, C, with another string, which is given by A plus B. A and B are other strings, and again we're using double equals. What's going to happen? It's going to print false, because in this case the things on either side of that double equals are object references, and when you compare object references with double equals, the question you're asking is, are these things the very same object? And C is not the very same object as the result of putting A and B together. What about this one? This is the same, except that now we're using the equals method, as I said at the end of the first part. Well, actually, you've seen exactly this example before. It prints true. When you want to compare the states of object instances, you use the equals method. It does rely on a sensible equals method having been implemented. We'll say a bit more about that later. We need to say a bit more at this stage about primitive types and the relationships between primitive types and classes, because you do have to understand how these things fit together in Java. You might wonder why Java even has primitive types like int and double. Why isn't everything a class? Now there do exist languages, Smalltalk for example, where it is much more the case that everything is a class, and that's very convenient for the programmer. Primitive types were originally included in Java essentially for efficiency, and it does give us a certain lack of uniformity in the language, but it was necessary at the time. Okay. There are some things which can only be done with objects. And the classic example is comes when you want to be putting things into collections, which you're going to meet later on. It turns out that only objects, only instances of classes, can be placed in collections. And so that can be a nuisance. If you want to put an int or a double or something in a collection in Java, you can't do it. We get round this problem by having for each primitive type a wrapper class. This is provided as part of the language, and it is nothing more nor less than an object that contains an element of a primitive data type. Okay, so we can have a capital I integer which simply contains the int 7. Okay, and it's for no other purpose than to say sometimes you just really need it to be an object so that you can do objecty things with it, like put it into collections. Now, these days the language is very good at punning back and forth between primitive data types and their object wrappers to such an extent that you as the programmer will actually rather seldom have to do this moving back and forth between the two things yourself. So in earlier versions of Java, we used to have to write things like integer I equals new integer out of 7 if you wanted to have an integer that would contain the value 7. Actually, you never had to write exactly that, but there were cases where you might write things a bit like that. And in fact, the slides in the state I inherited them this year had a whole bunch of examples that had that kind of thing in them, and I've taken them out because it's now officially deprecated to write this kind of thing in the Java language, which is to say the language designers say you shouldn't do it. Why shouldn't you do it? Because it isn't necessary. because Java these days has auto-boxing and auto-unboxing, which is to say, actually just, the language will look at what you've written and it will do what you mean with regards to the types integer and int. So for example, if I write integer num equals 5, well, the digit 5 there represents a literal of type int, but actually the compiler can see perfectly well what I want there. What I want is an object of type integer, and I want it to be wrapping up the int 5, and so it will just do it for me. Okay, so that line works perfectly well in Java. And similarly, if I end up by some means, doesn't really matter what means, with some integer object, so in this case I've said perhaps it's what's being returned from some method of my object, perhaps my object is a collection and I'm grabbing an integer out of the collection, say. Then I can perfectly well add that integer object to the literal integer 10 and assign the result to an int, because the compiler will just say, num, okay, we're supposed to be adding it to 10, well obviously we have to grab the int out of that integer object in order to do that, and it will just do it for you. It will do what you mean, which is great, except when it doesn't and you get confused. The main circumstance in which you need to be aware of what you're doing is if you are writing a function or a class and you're doing it to a specification given by somebody else, for example given by an examiner, and it tells you to use int or it tells you to use integer, then you must use the one you're told to use and not the other one. Okay. Now what about this? If we have two integer objects and we set them each to 5, I've just said that that works perfectly well. And then we ask whether those integer objects are the same using double equals. Well, you might expect it to say false, mightn't you, because they're two objects and they're not the very same object. But actually, this prints true. Why does this print true? Well, it's a thing called interning, and it's to do with the fact that that literal 5, which is visible to the compiler as being in the source code of your program, gets cached, and A and B turn out to be references to that very same object. They're just both references to the same copy of the literal 5. And so when you ask, are these references referring to the very same object, the answer is yes, they are. They're both referring to the same literal integer 5. Okay. Next example. This one's just the same, except we've got the number 200. Well, your first thought might be, you know the answer to this one because it's just the same as the previous example with a different integer there. Your second thought might be, why is she giving me the same example with a different integer there? It must be because the answer is different. Your second thought would be right, the answer is different. So this caching process that I just talked about only works for these small integer literals between -128 up to 127. Just a curiosity which you might occasionally trip over. What about this one? This one we're doing strings, and we're comparing two strings, both of which are set to the literal string "this is a test", and we're using double equals. This one prints true as well, because string literals are also interned. The compiler saves space by saying, we've got two copies of this literal string "this is a test". We don't need to allocate separate memory to these two copies of the same literal string. We can just have one copy, and we can have those object references, A and B, refer to that very same object. And so then when we ask, are A and B referring to the very same object, the answer will be yes. Okay, so that's what's going on there. This example is subtly different in that instead of setting A and B to be equal to the literal string "this is a test", we're setting them to be equal to a new string object constructed using that literal as argument. This time the answer is false, so if you explicitly use a constructor, your instructions are obeyed. You asked for two different object instances, you get two different object instances. So in summary, how do you compare things in Java? For things of primitive type, you use double equals. It's your only option. It's the one that works. That's what you do. For objects, you have a choice. You use double equals if the thing you want to know is whether two references refer to the very same object. But more often, the right thing to do will be to use the equals method. That is to say, you'll send the equals message to one of your objects with a reference to the other as the argument to the equals method. Now, by the magic of inheritance, which we'll come to later, every object in Java understands the equals message, so that will always work. The question is, what will it do? So it may be that the writer of the class you're using will have implemented the equals method in such a way that it compares the states of the two objects of that class in a way that makes sense for that class. So it'll be saying, okay, these object references might not be pointing at the very same object, but do they actually have the same state at the moment? Okay. And there are rules about that the person who implements the equals method must obey in order to make sure that the behavior of the equals method is actually sensible and won't lead you astray if you make reasonable assumptions about what that will actually do. And the chief one of those is that if two references are actually pointing at the very same object, then the equals method must return true. Okay, but the reverse is not true, as we've seen in several examples already. It's possible for things to be equal, but not double equals. Okay. By the way, if nobody in your class hierarchy, which we'll explain later on, has actually provided a specialist implementation of equals, then what you get is the default implementation of equals, which is just the same as the double equals method. So that's why there always is one, because that's always a possible thing for your objects to do. Okay. Now, we're going to say a bit about class methods versus instance methods next. So you've already seen some examples like this, where we are going to use a method that's associated with an instance of a class. In other words, we're going to send a message to an object using a reference to that object, and the name of the message will be telling the object which method to invoke, and it's not exactly calling a function, but it's jolly similar to calling a function. Okay, so we're saying, hey, my car, start your engine. And you do that using the syntax that you've seen already. You use the dot operator on the variable that refers to the class instance. What about this? You've seen this kind of thing before, and it's slightly different, right? So if you do something like math.random with a capital M, that's not exactly the same thing, because capital M math is not an object, it's a class. And so in this case, you're using the dot operator on the class name itself. So what you're doing there is you are invoking a class method. It's just one of these static methods, like the main method that you were writing all along before this lecture. Okay, and I said at the time, I think when we were talking about class methods, that actually instance methods is the commoner kind in Java, even though we started with class methods for compatibility with Haskell, which most of you had studied before. So in summary, we have instance methods which are associated with an object. You have to know which object you want to be sending the message to in order to get an instance method invoked. And we have class methods which are not associated with any particular object, they're associated with a class. And there you give the class name. So although these things look syntactically extremely similar, they're really doing quite fundamentally different things. What else is there to say? Yes, I mean, class methods are, they're globally available, even if you haven't got an object, provided you can import the corresponding type. They're also called static methods, and that's because of the function modifier that you use when implementing them, as you've already seen, for example, in implementing a main method. This is about static behavior, but there's also static state, and that's useful particularly for constants. So let's just see an example of that. So here's a classic example. We're going to have a class, we've called it math helper, and it's going to contain a public static final double pi, okay, which we can then use in some other context using the class name as before. This is quite helpful because it saves us duplicating the digit stream of pi and having to remember how many decimal places we wanted it to, and so on, everywhere. What else is there to say about this? Yes. Okay, so remember that the static is telling you that this is associated with the class, not with an object, and the final, which we saw in a previous lecture, is telling us that we don't expect the value of this thing ever to be changed after initialization, and we would like the compiler to complain if anybody tries to change it later. Okay. So, in summary, why should you use object orientation? You don't have to, of course, it depends on the context, but it has kind of taken over the world. Okay, so most modern programming languages now do incorporate some degree of object orientation. Why is that? Well, we claimed that it's well suited for supporting good software engineering practices. Okay, in that it allows us to use objects to model real-world entities and correspondingly classes to model domain concepts. And that's a good thing, I claimed, because the domain concepts change more slowly than specific functional requirements do. And so the effect is that what object orientation is doing is putting things together that change together as requirements evolve, and therefore making it easier to manage change, which is the thing that makes software engineering both hard and interesting. And if you do software engineering courses later in the degree, we'll have a lot more to say about this. A Java-specific summary, we've seen that variables can have primitive types or reference types. You've been working with primitive types all along. Now we've done some more thinking about reference types. We know that classes are reference types and also that all array types are reference types. They behave similarly in the sense that you create instances of them using new, and that the references means that we are referring to a representation in memory. It's possible for two references to refer to the same memory location, and you can copy the reference without necessarily copying the state of the thing that's being referred to. What this means is that you have a choice sometimes about what you really mean when you say, are these references equal or not? Sometimes you want to mean, are they referring to the very same object or the very same thing in memory? And sometimes you mean something coarser than that. You want to mean something like, do they have the same state? And object behavior can be expressed using class and instance methods. Okay, reading. The Java tutorial, it's not possible to point at something that's ideal for reading to recapitulate this lecture, because the Java tutorial does things in a slightly different order. It's never wrong to read it, however. It would be quite sensible to read as far as the end of chapter 4, but in doing so you would meet things that we haven't covered yet, so up to you whether you want to do that or not. If anybody's using objects first, chapter 1 is a good thing for looking at, because that's a pretty good fit for this lecture. And of course, if you have another book that you prefer, or something you're reading on the web, it's all good. There's lots of Java learning material. You should just use whatever you find helpful. And that's a good place to stop.